Nothing. All right. So I will share my screen. So I did have a question for most of you, though half the class missing, that makes this hard. If I required you to install a virtual machine on either a laptop or desktop, could you do that?
I already have it.
Already have it, good.
Yep.
Last semester, I had several people say, no, I couldn't do that. I have no disk space left. I have no whatever. So we're gonna try to do that. Next week, I'll talk about that and show how to do that and everything. Because there's a couple things I want you to do, but it'll take maybe 20 gigabytes of disk space. So,
You're not gonna just toss us out there and have us figure it out for yourselves, are you?
yeah, no. I'll show you what I'm gonna do, how to do it. And then just a couple examples of things I want you to run on it. That would be helpful, yes.
Is this like something like if you don't do the most cybersecurity classes, you can get that one? That makes sense.
If you don't plan on doing any more cybersecurity classes, and you're not a computer science major, and you don't want to do that assignment, I'll find an alternative. Because same thing happened last semester, and I know there was a couple people in that situation. So what I'll do is I'll figure out what that alternative is. Last time I didn't do the alternative, and the student's alternative was not turning the assignment. It was a 50-point assignment, so that hurt their grade. So I don't want to do that again. Okay. Thank you for asking. All right. In operating system security, when I'm thinking about what the internals of the operating system are doing, one thing, like I mentioned, is it's trying to prevent one process or program from affecting the memory of other processes. There are several different built-in hardware protection mechanisms. So things built into the CPU, the microprocessor core, that the operating system can take advantage of. Here's a list of them. I will talk about some of these. Or maybe all of them. So fence, it's kind of like what it sounds. It's a barrier. The microprocessor has a special memory register called a fence register, or maybe just a predefined address. And user programs go on one side. So the fence, if it's like 1,000 or 10,000, user programs are above 10,000, system programs are below 10,000. Or you can actually use the fence register to move where that is. The hardware looks at it, and basically what I should mention is when hardware is running in a standard microprocessor, there are different modes of operation. The most basic is user mode versus system mode. And so when the microprocessor is running, it first starts up in system mode. It does all the boot and operating system. And then it says, I want to run programs for the user. I'm going to switch to user mode. User mode is more restricted. There are things you can't do in user mode. And so, like setting the fence register, I could say, hey, the fence register has this new value. And I'm allowed to write to anything above that value. Well, in user mode, you're not allowed to do that. It's stuck. And when it's executing, it says, oh, I'm in user mode. I'm not allowed to write to anything in the low numbers. That's an example of what it does. Managing memory, loading and running processes, things like that are typically reserved for system mode. And there's a bunch of things that can happen. Now, as a user, I can ask the system to do something for me. The operating system will check, says, yeah, okay, I can do that for you. Switch the system into system mode, do whatever it needs to do, then switch back. Now, fence registers were typically designed for single user operating systems, because if there's not more than one user, you let the user interfere with themselves all you want, but they can't affect other users. If the operating system gets bigger, the address of the fence could not be changed if it was hardware fixed. So that ran into a problem. The initial ones, they just picked an address. But once the operating system got too big, they had some issues. Very old technology, but the concept is still there. So like I said, that was a specific fence. The fence register, now we can change where it is in memory, same type of thing. But if there was more than one user in the operating system, no protection for a user from other users. Also, no protection between programs. And so if I ran two programs, one could interfere with the other. And when I was doing this way back in the day, with the original MS-DOS, so that was back, was it MS-DOS? Yeah, and Tris-DOS, which was Tandy, Radio Shack, disk operating system. We're talking stuff in the early 80s. When I created if I wanted to load more than one program at a time, I had to give it different memory addresses, because as I was talking about the virtual memory, we didn't have that. So I'd say this program starts at address 10,000. This program starts at address 20,000. And I better be right. And then inside my program, when I ran it, I'd specify memory addresses to modify. I did them relative to the start of the program, so I wouldn't accidentally overwrite the memory of the other program. Typically, I just stop one program and start running another. If I wanted to improve the situation and have multiple processes or multiple users running at the same time, there was a concept called base bounds registers, where basically you say, here's a base register. For the current running program, we set that value, and the bounds, how far it can go. So start at 10,000, add 5,000 bytes. That's as far as it can go. Nowadays, no program's that small. Back in the day, my first computer that I bought had 48K of RAM. And I could do a lot on it. And 16K of ROM, dual 180K floppies. I had the high resolution of 192 by 128 graphics. I got through college on that machine. That cost me $1,200. And I got it on sale. That was a Radio Shack Model 3. I did not buy, my third year in college, they had this new thing. I had dual 180K floppies, and they came out with hard drives. Because it was either the floppies or use a tape backup to cassette tape. I backed things up on. And I was like, oh, hard drive. I could store so much more than on these floppies. But I didn't have the $500 for the 5 megabyte hard drive. It's like, this is a 2 gigabyte thumb drive on my keychain. Cost me a whole lot less than $500. Times have changed. Anyway, the base bounds register. So in system mode, so when I'm switching between programs or running a new program, you switch to system mode. System mode modifies the base register. So, okay, now we're running this program. Here's its base register. Here's its bound register. And then it starts running that program, and that program is limited within that base and bounds. When we change between these programs, that's something we call a context switch. That's what's down here. Okay, I'm not highlighting it very well. What happened to my, there we go. Okay, that didn't work. It's supposed to be the, I'm not seeing it, so, okay. Well, anyway. Yeah, that doesn't work, not very good color. Forget that one. Okay. Anyway, we call it a context switch, and the operating system is there. It's like, oh, we're switching a new user. Let's change all the information I need in the microprocessor so that now it's for this user running, this program running. What's the base register? What's the bound register? What's the user ID or the ID we're using for the user running? Some of this the operating system keeps track of, and some of the microprocessor keeps track of. We'll talk about some of that in CS150 and more in CS240. You guys don't have to worry about those right now, but it's there. Now, what's important is this does not separate programs and data sections. So my code and my data are within the same base and bounds, which means if I read in user input, I ask you to give me your name and you give me a really long name and I overwrite somewhere in my memory, I could overwrite part of the program with it if my code is not well done. So data can overwrite code, that's not good. Actually, I think it's cool because it's a runtime patch of your code. As it's running, you're patching it. It's like building an airplane when you fly. It's really cool. Okay. Does anybody ever do that? Build an airplane when you fly? No, why not?
Rockets kind of,
I don't think I'm
right? We
sorry.
separate first, second stage, third stage. You're in flight. You're not just like building it.
Okay, so rocket kind of falls apart as you fly it, but you know, a controlled separation, but you're not building it, you're debuilding it, deconstructing it.
Space station. Isn't
Space station, they're
constructing
building it,
that in
okay.
flight?
So we are building the space station as we use it, good point. So people do some of this. With computer science and information systems, we're doing it all the time. We're rebuilding them as we're using them. Roads, we'll do that. We build them as we use them. Airplanes, probably not. You know, so there's some things where we do this and we have to understand when it doesn't make sense to do it, when it doesn't. Okay. But anyway, I digress. Segmentation, it was a concept that said, hey, let's break the program up into multiple pieces, each of them having different access rights. So the code is readable and executable. And that is important to understand. It's not just executable because you got to be, microprocessor has to read it, to read the instructions before it can execute them. But data is readable but writable, but not executable. So you say, hey, the program, when I tell the program to run an instruction at a memory address, it'll look and say, no, that's in the data segment. I don't want to do that. So we'll have a code segment, a data segment, often a stack segment is something different. We may have data segment 1 and data segment 2. So the Intel microprocessors took this to heart and said, we're going to do this. We had code segment, data segment. Let's see, CS, DS, ES, FS, SS. So code, 2 data segments, D and E, a code segment, and a stack segment, at least. And different ones may have different rights. One code segment or data segment may be, this is my read-only data segment. This is stuff, these are the predefined strings in my program, the predefined data values that never change in my program. I'll put them in the read-only section. And then here's the stuff I'm dynamically creating, and I'll put that in the read-write section. And so one will be a DS section, one will be the ES section. Almost nobody uses those anymore. Okay, but they're there. There is a segment translation table maintained to locate the different pieces. And what you can say is, I want write to location 1 in the data segment versus write to code segment or read the instruction at code segment address 1. And they're different. So my program is talking about address 1 in both locations, but in different segments. So the segments become relative. And the program, what it typically does is says, okay, the code segment is an address in real memory, and I add to it your address in that code segment. So it starts at 10,000. I say address 1, so address 10,001 in the main memory is what I'm looking at. Data segment maybe at 20,000, so look at address 20,000 plus 1. And the hardware adds these together. You're saying, oh, code segment address. Hardware just adds it up real quick, calculates the real address, goes out to memory, grabs that real value and uses it. And this way, no matter what I'm doing, as long as I'm doing the right segment, I can't mess up with the others. Now, like I said, nobody ever does it anymore. They're kind of built into the system, but we set all the segments to starting at 0. All starting at the same location, so it doesn't matter. We have a better way of doing it, actually. And so the nice thing about segmentation, though, before we get this, I could change the segment to any location. The operating system would say, oh, your program's running. You're going to start your code segment at section 10,000 line or address 10,000, your data segment at 20,000. The next program running will start code at 30,000 and data at 40,000. And it could be two copies of the exact same program and both say, hey, I want address 1. Let's write to address 1. So data section 1. And the first one, it's address 20,001. The second one is address 40,001. The program doesn't see a difference because now the operating system has hidden that away. It's virtualized that. And it says it's relative to your segments. And that got people thinking that's cool. We can do more with this. And again, each segment has its own access rights. This is a read-only section. This is a read-write section. This is an executable section. That's cool. Two or more users could even share access to a segment. If I have two programs running, communicating with each other, I'll give you read-write access to a segment and you read only. So he can write what he wants and you read it. That works. And then maybe another segment goes the other direction and you have bidirectional communication. That's useful. Or what if we're running a program and we want to execute some standard libraries? Like everybody has a print function. Everybody has the square root function. Everybody has all these other pieces of code. Typically, we build them when we build our programs in what we call a library. Why don't we put the code for the library one place in memory and everybody can read that same code? You know, so it'll be physically in memory location 5,000. But for you, I'll put it at your location 10,500. Well, I said location 5,000, so I'll put it at 15,000 for you and 25,000 for you and 35,000 for you. And that's where your addresses think it are, but they all use the same place. And then when that code accesses data, well, it's relative to your data segment. So that library, that standard thing, when it's calculating square roots, calculates the square root for your data and for his data somewhere different, but we share the code. That's a cool thing. And we do this all the time now in a slightly different way. So if you've ever seen in Windows a DLL, dynamically linked library, in Linux, it's a shared library. The operating system loads that library to one place in physical memory and then gives your programs access to it. And so everybody who's using it uses the same piece of code. It saves memory. You know, I don't care if that's 1 megabyte or 10 megabytes in size, that library, and I'm running 500 programs that access the 10 megabyte library. It's not an extra, 500 times 10 megabytes in size, 5 gigabytes in size. So I'm not doing that. And this is something you think about when you're thinking about microprocessor system designers, software designers, operating system designers, programmers. We want to do things to save memory. We want to do things to allow isolation and separation. At the same time, we want to do things to keep it secure. And we want to do things to make it easier on the programmers and the developers. Now, we have to be careful. You can tell I'm segueing into a story here. Back when I had that first computer and it had all this whopping amount of memory, and I had been using one with even less memory before, I would write my programs in a language called BASIC. It's a beginner's all-purpose symbolic instruction, whatever. It was Microsoft Basic. The program was stored in memory. The system would read the program, interpret it, and execute each instruction as it sees it. And then that would, read and write stuff also in memory, which meant if my program was really big, it took up a lot of my memory. Especially the first machine I used had 4K of RAM. Ran at a whopping 1 megahertz. Megahertz. The one I bought was actually 4 megahertz. So it was much faster. So I kept my variable names short because longer variable names took up more space. Every character took up an extra character, extra byte in memory, and I was very limited. So X1, X2, X3, those are my variable names, right? And as I wrote the code, I didn't put in extra spacing because an extra space, took up a byte. So I kept it really limited. I go to college and I now taught this language called Fortran. Fortran's very different. You take the code, run it through a compiler to create the executable, and that's off running somewhere else. As separately, your code is stored on disk. Your code and the executable aren't in memory at the same time. But I wrote it the same way I wrote. All these tiny variable names, no indents, no spacing. I turned it in, it worked perfectly, and I got a 0. And I went to the instructor, Dr. Carol McNamee. I still remember this after 40 years. Okay, 39, excuse me, because this was in 82. And I said, I did, it works right. Why did you fail? She says, because it doesn't work. It's not usable. I said, what do you mean it's not usable? Where's this just stop? I guarantee you, as time progresses, I said, you know, she said, look at this. It's unreadable. You've got all these unusable variable names, X and Y. You're not saying, you know, name and date and identifier and number and index. You're just saying X and Y, you know, that's useless. And there's no good indenting, so I can't read this code. And I said, but I'm trying to save memory. And she says, I guarantee you, as time progresses, memory will get cheaper, computers will get faster, and programmers will get more expensive. So make the code readable and understandable by future programmers. Boy, she was right. I knew her for the next 10 years. That's why I know her name. She was I guess she was an instructor. She decided to go back and get her PhD at the same time I went to get my PhD. So we sat in the same lab together for a couple of years, and then she went off faculty member. So one place, I went elsewhere. She's now retired and gone. I'm still here. But she was right. And the code maintenance. At that time, a lot of people were thinking, we're writing code. You know, this is the late 70s, early 80s. We're writing code. And this code's going to be completely rewritten and replaced in 10, 15 years. No. Some of it is still being used today. There are existing libraries and tools out there that we just keep reusing. We're not going to spend the time to rewrite them and rebuild them. That has caused so many problems. Now, most of you probably don't remember the Y2K bug. Most of you probably weren't even alive for the year 2000. A lot of programs, to save memory, were storing dates, the year of the date in 2 digits, 78, 79, 80, 81, 82, 99, 0. Okay, so how old is somebody when you get to that 0? You take the current year, it's a 99, you subtract their birthday. So, you know, 99 minus 82, okay, they're 17. 0 minus 82, uh-oh. Also, a lot of people would put in their data sets flags. We want to know, are we at the end of the data set? Oh, we'll just put 99 in there as a common value to use. So the year 99 was also a problem. So there was a massive government-wide, industry-wide, worldwide reprogramming effort for the couple years before the year 2000 to remove anything that depended on this 2-date value where the 00 would break the world. So it was the Y2K bug. And there was a massive investment worldwide to fix that problem. Okay, because people were trying to save memory, not thinking about maintenance of the stuff 20 years later, 10 years later, 15 years later. We are now, right now, this happened, I remember in the 90s, it's happening, and early 2000s, it's happening again. I was just hearing a news story. They say we are in a period of mass resignation. People are changing jobs at a record number right now. Why? We finally got out of our Zoom closets. And during this last year, people were really rethinking our lives. Some were thinking, you know, I don't want to do this for the rest of my life. I'm going to change careers. Others, you know, I really don't like my boss. I don't like the way my company's treating me. I want to get a different company. And I know this company across the street is desperate for people and they're paying me $10,000 more a year. I'm going to hop across the street. The same thing happened during what we call the .com era, when all the internet was exploding, everybody was starting to create things, and they were desperate for programmers. I remember I was at one company working with them, consulting. I go in there. I think I mentioned this before. Actually, I went up to the break room. There's a couple of guys playing pool. I go to my meeting. 2 hours later, come back, they're still playing pool. I was like, how often do you guys have breaks here? You're playing pool. Oh, I said, I saw you 2 hours ago playing pool and you're playing again now. Oh, we've been playing all afternoon. Don't you have jobs? Well, they hired us, but they have no work for us yet. We got all this investment money from the investment bankers for the company to hire a bunch of people, but they don't actually have the work to do. But they didn't want to lose us. Eventually they did lose those people, but so we're seeing these changes. But the issue is, you go across the street to work for another company, he gets hired by your company and looks at your code and says, I can't read this. I don't know what his code is doing. And they want him to improve on your code for the next feature release. So we talk about documentation, we talk about inline documentation, commenting your code. Do that to make it easier for the next person. And hopefully somebody will do that for you. So when you go into the new job, you'll look at the code and say, I understand this. It's something to really think about when you're configuring the system. Here's one more. This was a friend of mine, Matt Bishop, ran into this. He was hired by a company, this is the late 80s. They had a big security problem. He scanned the system. He found the problem. He fixed their code, fixed their problem. 5 years later, they call him back. The problem's reappeared. He goes and he remembered where it was, goes and looks at the code, and sure enough, his fix is gone. Basically, somebody had gone in to the job, looked at the code, and said, I can do this more efficiently, not realizing their more efficient was less secure and caused the security problem again. What he had forgotten to do was write comments in the code saying, this is implemented for this security fix. Do not do it this other way. Or this is why this is done this way. Maybe appear less efficient, but it's the only way to be secure. He learned early on, this is the early 90s, you've got to put that comment in there because people will go in and change codes. You will see it yourself on your own code. You will also, I guarantee you, when you're working on a system, either developing a system, configuring a system, or actually writing programs, you're going to make changes and it's going to break something. What do you do next? Okay, this happened to me yesterday. I was working on some code on Monday. Yesterday, I went and made a change to it, said, oh, I need to have it add this extra feature, and suddenly it stopped working. Oh, shoot, I accidentally deleted too much because I had completely replaced a function, deleted the old function, or not completely replaced a function, but anyway, I was cutting and pasting and changing a function or whatever, and suddenly it wasn't working. The lines of code were gone. What did I delete? Well, I have a practice now. Before I do that, I say, I want to fix this function. I copy the whole function and I comment it out. It's now on the comment section. Then I do all my changes. And then I test the bejeebies out of it. And if it works, then I can get rid of what's in the comment section. But if it doesn't work, I've got all my old stuff there right in that code. Now, also I save version numbers. I save copies of other places as I archive things. I use GitHub to store things, which keeps, every time I do a major change and have tested it, then I upload it there. So if that test I finally realize broke things, I can go back. But if you don't do that, I can waste so much time trying to remember what that old code was I deleted. Now, for me, it was Monday's code, so that wouldn't have been too bad. But there's one piece of code we've been working on for 5 years now, on and off. And if I change something in there and I don't even remember why it was there to begin with, I'm going to forget it. And this leads to security problems as people make those changes and break things. So good practice, document it all. If you're reconfiguring the system, what was the old configuration? Keep that documented. It's a pain, it's extra work. It saves you so many hours that one time you made a mistake. Okay, so over the last week or last month, I spent an extra 10 hours documenting everything, but I just saved myself 50 because of that one mistake. So I want you to think about this. Obviously, I digressed away from memory, but Programmers and developers of operating systems are trying to make things easier, keep you from making these mistakes. And like I said, the separation and segmentation is one way to help it. If they do this for me, I don't have to do it in my code. It makes my code simpler. Okay, so I have to get back to this. That's right, I was talking about this thing. Sorry. There are limits to doing segmentation. The operating system needs to maintain a segmentation translation table. Which segment has which starting address for which user or which process? As we do a context switch, we got to update all those segment registers. We have to maintain the length of the segment and make sure it's compared with every address generated. Well, what if I need to make a segment bigger? What if I didn't give the user enough space? Is there an ability in the operating system said, that's okay, I'll give you more space? Well, segments have to be contiguous in memory, a base and a bounds. Well, that next program was right after your segment. There's not space. So I have to find other place in memory, move your code over, move your segment over. Now this, I have to copy it. That takes time. Give you space. Well, now that space you were using is now available for somebody else to grow into or be allocated to. But as you can see, what's going to happen here, it's going to be like a puzzle. We're going to move things around. We're going to start having gaps. As I move, segments are all next to each other, we're good, but as soon as I need to move one, I have a gap. As somebody fills in it, I have a smaller gap. I have gaps here and here, and that's called fragmented. So as we're adding and deleting and moving things, space becomes very fragmented. We lose access to some of this memory. We want to make that better. Same thing happens on a hard drive. As I create a file, the next file goes in the next location. Well, I made my file bigger. I wrote more in my Word document. Oh, it doesn't fit there anymore. What do I do? If I want it all in the same place in memory, I got to shift the whole document. And now I've got a gap, a hole. Somebody has to allocate and use that hole. You may have heard of the term of defragging your hard drive. That's to get those holes gone. Also, the way we solve the problem with files, at least, is it keeps track of chunks. Well, here's chunk 1 of the file, here's chunk 2, and I'll allocate you new chunks different places on the hard drive. Well, now if I want to read the whole file, I read from here and then here and then here and then here, and that drive head is bouncing all around. Not a problem with solid state drives, but with physical drives. Or if it was a tape drive, even worse, because you're going back and forth on the tape. Slow things down. Defragging puts everything in your file together in the same place, so it accesses the file altogether. Same thing will actually happen with hardware, with RAM. But we fix this problem. We use a concept called paging, where basically we take all of memory and we break it up into chunks. The typical page size we use is 4K. So 4 kilobytes in size, 4,096 bytes, 2 to the 12th. And we say that's a page. And I will allocate things to you in pages. Let's see, actually, do I have? No, I don't. Okay. So I will allocate things to you in pages. And what I do is your code, say, needs 3 pages. So here's page 1 in memory. Actually, let me do this differently. So here's memory, and I break it up into pages: page 1, page 2, page 3, 4, 5, all these different pages. And I'm sorry, my lines are really sloppy, but these are each at 4K boundaries. So 0 to 4095, 4096 to 8191, etc. The operating system uses, so your address here, say it's 32-bit address, right? I have 20 bits that mention the beginning, the page start address, and then 12 bits, so I'll have 12 here, that tell me which byte inside the page I want to access. Because it's 2 to the 12th is 4096. So this is on my lower address. This tells me what part of the page. This tells me the page. So if I really had real memory, I'd use those 20 bits, and again, 32-bit address space, so I had 64 bits, it'd be bigger, it'd be 52. These bits tell me the page number. Well, what the operating system does is we have a lookup table. When my program is running, it takes this page number for my program and translates it to some page start in memory. We call it a translation look-aside buffer. So as the CPU is running, the TLB, I go through and I say, here's this page. That's where it is in memory. Let's just change these first 20 bits, replace them with the one in the lookup table. That's the actual physical place in memory. So my code, I could actually have A, B, C, D, these are the pages in order in my program, but they appear anywhere in memory. My program accesses them, this would be 0 through 4096, or 4095, this would be 4096 or 8191, and the hardware just bounces it around. Which means I need more space. It finds available space in RAM and says, that's yours. You need a page, here it is. You need 2 pages, here they are. If they're together, I'll put them together. If they're not, that's okay. I'll give you a page here and a page here. Put it in the translation look-aside buffer and we're all good. Yes, we still have fragmentation, but this is all in memory. So we're just doing this translation, always doing the translation. It's fine. There may be blank space at the end of a page because you may have only needed 1,000 bytes and I gave you 4096, but that's only at the very end of that program for you, or that section of memory, because I'll do this for code and then I'll do it separately for data. And I can do that. And each page has different permissions on it. Usually we glob them together and say, this is all your code pages. This is readable and executable, but not writable. Here's your read-only data. It's readable, but not writable or executable. Here's your read-write data. It's readable and writable, but not executable. Here's something that's everything. Those are dangerous, but we have them. And actually the operating system could, as it's loading, it says, hey, these are my pages. I have complete control of them. They're read, writable, executable. I copy your code into it. Then I get rid of the writable permissions when I give it to you. So access rights are on the pages, but we can bounce them around. This is really, really useful. This is what modern operating systems do and modern hardware does. And like I said, the default is really a 4K page. And now the cool thing with this is I said, you're running your program, says, okay, my start address, my first instruction is that address 0. I say, okay, here it is. That's your first page. There it is. Somebody else is running their program and their first address is here. Let's do C here and D here. And they say, I'm at address 0. And it says, okay, you start here at address 8192. And the other person, is, oh yeah, but I'm at address 0. Yeah, but your address 0 is really address 0. And it doesn't matter. Your programs don't see a difference. So every program can be compiled thinking it has access to all the memory. And the operating system decides where to put them. Now it does a little more than this too, which we have to be careful with. Say I'm using an input-output device or a physical device, a disk drive, or a network card. How do I communicate with that network card? There are 2 ways. One is special instructions called input-output instructions, IO instructions. And I use what we call IO ports. And I say, hey, write to port 45. That is where this network card is. What people have gotten to is using actually memory mapped IO, where a section of the memory, usually way at the top, isn't real RAM. These are addresses that when we write to that address out on the system bus, the network card looks at it and says, oh, that's me. You wrote to address, FFFFF45, and that's me. I grab that and I use it. And when you say, hey, I want to read from address FFFFF46, usually we write to one and read from the other. It says, oh, that was me, I'll respond. And there's no real memory there. But we can virtualize that. Piece of software can say, hey, I want to read and write from memory mapped.io at my FFF or EEEEE, whatever, and it translates it to FFF. So we usually have this, and it's usually only the operating system that deals with those or device drivers for the operating system. But paging allows us to do that real easily. And this memory translation buffers allow us to do this real easily. And that's all cool. What if I had like one of my older machines and I ran out of memory? What if I say, give me another page, and the operating system says, they're all used. You loaded so many programs, there's nothing I can do. Well, we have a solution to that. The operating system says, okay, well, this page hasn't been used in a while. I'm going to copy it to a place on disk, what we call a swap file, copy it over there, and now make that page available to you. When it comes around, eventually the program that was using that old page needs it again, we'll swap something else. That's not bad. The old way of doing this, we had something we called overlays in Fortran, where I had to say this code, it only overlaid code, not data. These functions, these files basically that I compiled are an independent unit. Here's another one. And if I had to run a function in unit B, unit A, all of unit A was deleted. Unit B was loaded into memory over the same exact memory. And then if I needed unit B again, unit A was all deleted, unit B was, well, that was usually many, many pages worth of code. And you had to be careful, hope something in unit A wasn't calling unit B, calling back something in unit A. You had to structure code real well. Well, with paging, I don't have to worry about any of that. It swaps the pages as needed. If I'm writing a very large program with one that needs a lot of data, scientific research, data science stuff, simulation and modeling, needs lots and lots of RAM. The moment I run out of RAM, it starts swapping. Access to disk is a whole lot slower than access to RAM, and it really slows down your program. I did an experiment with one of our machines once, where I created a huge array, two-dimensional array. Think of a matrix. And I filled it from beginning to end with a bunch of zeros. And then I accessed it from beginning, actually not a bunch of zeros, I think it was 0, 1, 2, 3, 4, whatever. Timed it. Then I accessed it, instead of going across the rows, I went down the columns. Well, this thing was bigger than memory. So whenever at the beginning, everything's in memory. Then when I got to the end, it started swapping pages. Well, the way arrays are stored in memory with a CPU, let me look at a two-dimensional array here. Let's keep it real simple. It's stored this way. This is byte 0, byte 1, byte 2, byte 3, 4, 5, 6, 7, 8. So if this is really wide, say 4,096 rows or columns, that's one page. Next row is another page, etc. So I set it up that way, 4,096 columns, so many rows. If I'm accessing this way, it accesses this whole page together before it goes to the next page. If it accesses this way, each access is a different page. Gets down here somewhere I'm out of memory, it swaps out this first page, swaps out the next page. Then I come back up and I start this next column, swaps out the pages. Really slowed down the program. Just the way I access the memory. So knowing how the memory access works and things really matters. I was talking to somebody who looked at a researcher's experiment here in one of like chemistry or somebody who was doing a big thing saying this is so slow because he had too much memory and swapping out to disk. And the guy looking at it said, oh, your order of access is wrong. Let's change it. Sped it up 10 times. So went from running for 10 hours to running for 1 hour. That's not bad. Because it's paging, because they didn't know this. Now, finally, they said, how do I stop this from happening? It's still too slow. Oh, get more RAM. Oh, yeah, because I'm needing 32 gigabytes of RAM for this program, and I have 16 in my machine. Yeah, get more than 32 and you're fine. Then it was down to 10 minutes. One of the programs I'm writing, when it analyzes the Chrome browser, it takes up 24 gigabytes of RAM to do the analysis. So that machine, I run it on my machine with 32 gig. I don't run it on my machine with 16. These are things you need to know. Now, as we're swapping, it goes on swap disk, that space is vulnerable if it's not protected. You just swapped your code out to disk. If I can overwrite your code, and then when you swap it back in, I own you. We got to think about these things. If while you're running at swaps and you found some way to actually avoid the paging system and access the real raw memory address, I own you. So these are things just to think about. We can combine paging with segmentation. This is kind of what people do, sort of. They don't really use the segment registers, but they do it logically. This is the code segment. This section of pages is read-only or readable executable. This is the data segment, readable, writable. So protection rights applied to the segments. Paging makes the implementation efficient. Segments are accessed through paging. You have to kind of keep extra track of that. Typically, we keep track based on what I showed in that diagram last time. We have our code segment, our read-only data segment, our heap, and our stack. And we just keep it that way. And when we load the program, the code segment never changes because you're not adding new code. The read-only data segment never changes because you're not writing new read-only data. The heap starts at one location, grows up. All we're changing is its length. The stack starts at the top and grows down. All we're changing is its length. And then values are contiguous. Actually, typically what we say is stack is, hey, here's a maximum size, no more than 8K, no more than 16K, something. Maybe it pre-allocates all the pages you need, maybe it doesn't. Question, paging, I'm swapping. You wrote your really sensitive, super secret chocolate chip cookie recipe in your page. You stop running your program, I run my program, I get your page. Or maybe we just swap and I get to see the page. Do I see your top secret chocolate chip cookie recipe? Let's go back to the object reuse. Probably, unless the operating system is a trusted operating system that zeroes out the pages when we swap them. Because sometimes it's like, okay, you had code or you had read write data in there. I want to make it to be a read write section for me that I haven't written to yet. I just say, hey, give me an extra 4K. So it gives me the 4K. I don't write to it, I read it. I want to see what you left behind. So again, paging makes things more efficient, allows us to do all these things, but there's the residue. There's the extra problem we now have to deal with because of this. Some operating systems will zero the pages, some won't. You got to think about that. Can your code do anything about that? No. You don't know what page you are in memory, and you don't know if it's being used or not. Unless the operating system allows you to lock it, you're stuck, yes.
Can't you get your code to clear out what you've written before you end it?
Well, my code, I'm using my program right now, and we run out of disk space, and it forces me to swap. In the middle of my program running, I can't do anything. Now, yes, I could be more careful and I could say, before I end my program, I'm gonna zero out my pages. And I've done that, but I can't zero out my code, but I can zero out the data. Some operating system will allow me to say, hey, sanitize this page before I exit. Or don't ever swap out these pages. They're critical. You know, if I'm in a real-time system, I don't want things swapped. If I'm doing cryptography, a high assurance cryptography, I don't want my crypto stuff swapped. That's my crypto keys. There's actually a requirement in the US government, if you're doing high level encryption, you have complete control of the crypto keys at all time. So you have to be running in a system that controls whether or not you swap or not. Controls how, you know, who has access to those keys. So yeah, no swapping. No other things while I'm doing the crypto functions. So I can delete the keys from that memory before you do anything with it. I put the key in, I do my function, I delete the keys. Now we can take this even further, and this is new work that people have been doing. Well, doing it for the last 20 years, but there's actually a microprocessor out now that does this. It's called tag memory. Let's reduce the granularity of the access control below a page. Let's do it per word in memory. So every 32 bits or 64-bit chunk has a tag associated with it. The first thing that they did with tagging, and this was Ed Sue as part of his PhD at MIT before he went, or was he at Penn State? No, he was at MIT before he went to Cornell. And what his did is said, when I read user input, I'm going to tag it as saying, this is tainted, this is dirty, this came from a user. And then when I'm executing code, if it says, oh, I want to jump to this address, well, where'd that address come from? Was this an address that was generated by the user data? Is it tainted? If it's tainted, no, we're not going to do it. Because there's so many vulnerabilities in our code where we override these buffers, we override pointers and addresses. We're doing runtime patches of our code. It's looking and said, no, I'm not allowed to do. That's tainted. We're not doing that. The Dover microprocessor, more recent project, and we've been researching it recently. Can do a lot more things. It can a lot of different types of tags, and it says not only user data, but maybe this is a sanitization routine or a crypto routine, or we're in a process control. We have to do process A, B, C. So this data is from process A, and before we have to finish A before we start B, before we start C. We can never jump from A to C. We always have to do B first, and they can do all that type of stuff. Extra work on tagging, extra work on propagating those tags is you add two values. What's the new tag? If they were different tags. How do you deal with that? Is there a way of sanitizing the tags? Dover's work is a coprocessor, sits on the same silicon, but sits next to the main microprocessor, monitors what it does, and does all the tagging as it does it. That's kind of what Ed Sue did too. And Ed, I say Ed because we worked with him on a project when he was at Cornell. They were doing an updated hardware version of what they were doing, and Dr. Song was doing her PhD, modifying an real-time operating system to manage the tagging and redefined new tagging types that took this single user operating system, made it a real-time executive monitor, and made it ultimately multi-user by just using tags and separating the users. And then Ed's group implemented it. That was a fun project. And then while we were doing that, the Dover group started doing their work. They made money. We're still here. Okay, now one problem we have, and this is where there's so much background knowledge you guys don't have, but as I mentioned, the buffer overflows, right? I read user data, the data is too long, it overflows a pointer, overflows an address. What can I do with that as an attacker? So the original things were, hey, I've got your buffer. I know where your program is in memory because your program always starts at the same virtual memory location because that's where you coded it. I overflow your stack. I've read the buffer. I overflow the return address. I make the return address when your function returns jump here onto the stack where I just wrote new instructions. And now your program starts executing my code that I just had you download and put into your machine. Well, that only works if the data in the stack is executable. So, hey, no longer have executable stacks. Hey, we win. Programmers, oh, wait, I got an idea. And I'll go over more of this later, but let's see. When we're writing code, if I call a function, like say the square root function, I say, hey, calculate the square root of 7 for me. Well, what happens is 7 is stored on the stack. Then the return address of this next instruction I want to execute is stored. Then I call the square root function and it can look on the stack and say, hey, what number am I supposed to be square rooting? 7. Okay, I'm cool. Well, if I overload this, when I return, it says, hey, what's the next instruction I should execute? That's this one. Well, if I overwrite the stack and tell it, hey, no, I want you to run something else, and I make it jump not to where I was, not to here, but to start of another function, that other function says, oh, well, you're supposed to tell me what to do. What's my parameters? What are you passing? Let's look on the stack, right? So if I overwrote that 7 also with some information, I could have this say, hey, I'm going to call the function that allows me to run a new program. And the argument above it, I'm going to write as the program I want you to run. Oh, your program happened to be running as this is your sendmail program. It's running as root. I now tell it, hey, give me a login shell. Well, that's a root shell. Here I am. I win. And I didn't make you, I had you call an existing program, an existing library routine inside your code. I didn't write new code. And your code is always executable, and I made you jump to something that's executable. And we said, well, we're going to find a way to fix that problem. And somebody said, instructions are really interesting. In Intel, your instruction may take 1 byte, 2 bytes, 3 bytes, 4 bytes in length. Some instructions like return says, hey, I'm done my function return is a 1 byte instruction. Well, I can jump to any address to start an instruction. So if I jump to an address and it can look like something else. But the important thing is I could tell this, hey, jump to somewhere here in memory. It's a bunch of instructions followed by a return. The return comes back to where I was, remove the old stuff from the stack. Well, the next thing on the stack is now what do I execute? Where am I returning to? I gave you another address to return to because I wrote the sequence of returns. And so it says, oh, I returned here, executed these. Now I return somewhere else in memory, execute these 3 things. I can patch together a whole bunch of different snippets of code, what do we call gadgets, and create a new program. And who was it? It was Michael Franz at UC Irvine actually wrote a compiler. He said, here's what I wanted to do. It said, hey, here's my program. If I string together these gadgets, it'll execute what you want it to do. Called return-oriented programming. Well, shoot, now you're not even calling special functions, you're just calling something in memory. But tagging can solve that problem because tagging would say, hey, this is not the start of a function. You're not allowed to call here. You're not allowed to return here either. Intel and ARM now implement things like that type of control flow integrity, they call it, to prevent the flow. So every time we fix something, the hackers come up with a new way to do something. It's really fun. Okay, we'll call that. Anyway, this jumping to somewhere in memory, this return-oriented programming, this jumping to an address of a different function, this jumping to where my code overwrote the stack, all requires me to know an address. Address space layout randomization says, how about when I load your program, I change where the stack is. It doesn't always start at hex B0, BFFFFFF and going down. I'll change that somewhere. Now, if I try to say, hey, I have this stuff on the stack I want to jump to, its location in memory has changed. But the code still is always in the same place relative to what I'm executing because I wrote my code, I compiled it, I said, hey, function 1 is at address 100, function 2 is at address 250, function 3 is at address 350, and I know how to jump to these. Can I fix that? If I compile my code in what we call position independent, which says, hey, I'm running this function, I want to call function 2. I know it's at address 250, but I'm not going to call address 250. I'm going to call, hey, get my current address and add 125 to it. Then I could take the whole code and shift it up and down in memory. I could have it start anywhere in memory, usually on page boundaries. And there's no hard-coded addresses, makes the attack, they can't do return-oriented programming because they don't know where those return addresses are, unless their return-oriented program is relative. They can't do jumping to a function to a known address because that known address changes. They found some ways around some of this, but it makes it harder. We're always making it harder on them. In 32-bit systems, there's not enough randomization with the number of pages and how much space we have and everything. People can try multiple attacks and finally guess what address you're using. 64-bit, you got a lot of space to play with. Most programs are much smaller. If code is not position independent, not enough randomization. Intel 64-bit is guaranteed to be a position independent the way they've written it, the microprocessor to work. It's very naturally supports this. 32-bit Intel does not naturally support it. You got to play some tricks. But you can do it. So attacks that use relative offsets, unless we find a way to shuffle the program. Every time I run the program, it's rearranged. That could cause a problem. There's one technique somebody's using where they're rearranging the program while it's flying. That's tricky. Slows it down, need a lot of RAM, a lot of microprocessor cores to do it. But this is a common technique that's out there now, this address space layout randomization, to say, and the operating system has to maintain it. It has to say, hey, I'm loading a new program. Let's adjust these addresses randomly. Let's set things up. Let's set up all the tables for this. Yes.
Do they use like true random, like the randomized addition?
So on the 32-bit, they randomize a certain number of bits in your address for the start address, but it's not fully random. So they say, we're going to keep the pages the same, so it'll be page offsets. We'll randomize it among 65,000 possible pages, that type of thing. But that's a good question. Random. There's no such thing as true random. Well, yeah, there is, but most computer systems don't deal, almost none of them deal with true randomness. It's what we call a pseudo-random number. We use pseudo-random number generators, which go through sequences of numbers. You give it a seed, you say start here in the sequence, the seed tells you where you start in the sequence, and you go long enough, it's a 32-bit random. After 65,000, you're back at the beginning. There are good random number generators, pseudo-random number generators, cryptographically strong ones and bad ones. Bad ones, it's much easier to predict if you get one value what the next one in the value sequence is. Cryptographically strong ones, you give me a random number, I don't know what the next one is. The non-strong ones, you can figure it out. The default ones that come with your, the rand function in C, the default random in the Linux operating system, those are not cryptographically strong. Actually, I'm going to not cover this part because it's going to take a little bit. Any questions on this? So earlier we talked about, I'll just hint towards these things. Identification, authentication. An operating system has to manage those functionalities. We talked about access control. An operating system has to manage that functionality. Who has access to which files, who has access to which memory. What I just talked about here, what it does under the hood in just managing the memory itself as programs are running. When a program's running and it wants to do something, is it allowed to do it or not? Can it send a message? Can it write to a file? Can it do these things? Depends on what the operating system controls. So we'll talk about some of that. What I'm going to move to on the next section is why I wanted to stop here. There are guidelines out there for strengthening what we call hardening your operating system. Basically, there's the default installations or implementations, and then there's things you can do to configure it to make them more secure. There are consulting groups out there, organizations out there, guidelines out there, and I'll share one of them that says this is the best thing. So thinking about identification, authentication. How do we authenticate ourselves normally in an operating system? Password. User ID and password pair. Identify ourselves with user ID, authenticate with the password. What restrictions are there for my password? How long is it? Can I do a 6-character password? Are there features like I have to have an uppercase, lowercase, and a special a number and a symbol in there? How often do I have to change the password? How long do I have to wait before I change it again? There's recommendations for that. 24, 14-character minimum password length. Have this level of complexity. You have to change it every 60 days, 90 days. You can't change it more than twice a day, or you can't change it more than once a day. Why would I want to do that? That's a good question. Why would I want to prevent you from changing your password more than once a day? Yeah.
If somebody had access to your system to change it to something that they
could use and then maybe change it back to the old one?
Right. Somebody breaks into your system, gets access, they change the password to something they want to use. They do things for a while, then they change the password back. You know, so you don't know that your password got changed. So anyway, we're going to talk, there's a whole lot of things, whole guidance on a whole bunch of things. Now, if you were at a community college taking a cybersecurity course, they'd spend a lot of time going over this and say, hey, we're going to set up a Windows environment for you. You're going to harden it. If you're competing in a competition like PRCCDC or CCDC, what is Collegiate Cyber Defense Competition. PR is the Pacific region, so it's the one that we're eligible for competing in. A lot of things they want you to do is harden. They give you a set of services, harden them. Make it so that they can't attack, can't break in. You know, bad default passwords, or the fact that there's default passwords, or bad password length rules, bad other things. Guest accounts. Hey, I've got an account on my system. Somebody can log in as guest, password guest, or no password, except the permissions are wrong and they're running as root. Oops. Or I think it's a single user system, but it has a guest, so I didn't set any access control on any of my files. Oops. Do we have default guest accounts on machines? Yes. Default guest account on a Wi-Fi? Yes. And a lot of Wi-Fi, there's a default guest login. U of I has a guest login for visitors. No, it's not a default, but it's a publicly one, but it's restricted what they have access to. They are not considered to be on the VPN. So that's an interesting thing. I talked about VPNs. This just came up. That's why I'm going to share this. I was trying to access what we call a dashboard. So it was a bunch of data about you guys, about students. They said, well, you have to access it from campus. Well, I'm accessing from my office. It's not working. Oh, no, you have to be logged into the VPN to access it. So it wasn't just campus. It was this VPN subnet I had to be logged into. Well, I was, but I was logged into the wrong VPN subnet. The one for my research lab. So it didn't let me get access to that until I switched to the other VPN subnet, the main campus VPN subnet. Then it let me get access to this data set. Well, then it asked me to log in as a standard user. So another level of, you know, just one more thing of restriction, because this was, it didn't show any names, but it was detailed breakdown of how many majors we have, the ethnicity of the majors, the genders of the majors, retention, how long people go, you know, that type of stuff. And they just wanted to keep that more internal. But I was looking at how many are cybersecurity majors. We have 45 of you right now. So we're trying to get that number bigger, but hey, 45 is not bad. Since I know we closed some programs last year with budget cuts that they'd been around for years, and they had, like, one of them had 25 students, 25 majors, and 5 faculty. It's like, well, we got 45. We're doing better. All right, I'm going to stop there. Any questions, comments, concerns? Okay.